In this session, we cover monitoring an OpenSearch cluster. What are the main metrics in OpenSearch to monitor and how to read the dashboards as they are shown on polls. I'll also provide various insights on what action to derive from them. Obviously, this is not a comprehensive guide, but it definitely covers the basics and common cluster behaviors. Also check out the next session where we take this knowledge covered here and discuss common OpenSearch issues and how to resolve them. Let's start with cluster health monitoring as provided by OpenSearch. There is this concept of cluster color state, red, yellow, and green. This is something that OpenSearch provides. It will tell you if it's a green state, red state, yellow state. What red, yellow, and green mean is the shard assignment states. So remember we had primary shards and replica shards. Red, yellow, and green would mean are all the shards assigned like I wanted them to. That means green. So all primary and all replica shards are properly assigned and loaded. Yellow means all primary shards are available and assigned and loaded, initialized. So we can search on them. But some replica shards are unassigned. Unassigned means we cannot find them. The cluster state knows that there needs to be some shards, replica shards, but it's unable to find them. Usually, in most cases, that means the wrong configuration. It means you have an index with 3 replicas assigned to it, meaning it looks to have 4 copies of the data, primary plus 3 replicas, but you only have 3 data nodes. So it doesn't have where to copy an additional replica. That's why it's yellow. That's why I'm also saying this green yellow is not really interesting. It's a good indication for your desired state not being where you want it to be. You're not at the desired state, but it doesn't mean anything beyond that. Red, however, means that we know that there's primary shards that are unassigned. This is a big deal. This means the cluster reports the cluster state is not being able to assign, or it has unassigned primary shards. This is data loss. So this is like a big deal. All right. It could happen for very few seconds here and there during initialization phases or relocations or things like that. It could happen. But if it happens for more than, I don't know, a couple of dozens of seconds, it's a problem. All right. And that's one of the alerts that we have built in Pulse, obviously. So that's one thing to monitor. But again, it's the thing that everybody talks about. But to be honest, it's probably the least important thing most of the time. There's other metrics that are important for us. CPU is one of them. But to be honest, it's not in the top 5, to be honest. But CPU is important because it lets you understand how busy your machine is. There's a better metric. I'll show that to you in a minute. But it shows you, how busy it is. On Pulse, we allow you to switch between average and max easily. So the average is really what's interesting here, but sometimes the max will actually show the issue if you're maxing out on CPU. So there's that. There's no really clear guideline here because some clusters are, I'll show that to you in a minute, but some clusters are an average of 20%, but it's an issue, right? Because they have performance issues. Some clusters are on a 60% and we can scale them down. It really depends on other metrics as well. That's why the CPU metrics is interesting to look at, but definitely not in isolation, and I'll explain. What we're saying here is that healthy cluster can spike to 100%, but the baseline, we want to see that at about 70 or 75%. The reason for that is because below that, it means that you're over-provisioned. And if you have performance issues, it's not related to CPU, and we'll talk about that. Above that, it means that you are obviously under-provisioned of CPU and you cannot sustain spikes on average. With max, we expect to see the CPU maxing out. So that's the CPU metric. Now, the more interesting metric, probably the most interesting metric, is actually the load average. And on Pulse, we draw the 1 minute, 5 minute, and 15-minute averages. That's also what being reported by OpenSearch. And the reason for that is because those metrics are really showing the load of the machine. The load average is a Linux metric. The load, actually, the load metric is a Linux metric that factors in CPU, disk, and in general I/O network as well, but that's negligible. And usually the load average will be high when either the CPU is very high or the disk usage is suboptimal, if there's a lot of disk usage. So the load average is a metric between 0 to the number of cores that you have. And let's say you have 8 cores, I would expect to see the load average at about 5, 6, maybe 7 on average, not more than that. I want to make sure that there is some leeway, again, for spikes and just to make sure that it's not always very busy. If the load is 8 out of 8, that means that you are working very hard. And we don't want that. We want to have some leeway. And that's why what we do, we measure those averages. So the 1 minute average will show you a lot of spikes. The 15-minute averages will be sometimes too shallow. So the 5-minute average is a good average to look at. And that's what we usually do. We want to see that the 5-minute average is at about 70-75% of available cores. That's usually what we want to see. And again, like I said, sometimes you can see that you are 7 out of 8 in load average metric, but the CPU is almost idle at 10 or 20%. That will immediately tell us that there is a performance issue with the disk, and vice versa. So maybe the disk is super smooth, but the CPU is working very hard, and we need to understand why the CPU is working hard. And those are usually this is the thought process. That's why I said the CPU on its own is interesting, but it's not too interesting. The load average metric is probably the most interesting one. And on Pulse, it looks like that. So we let you zoom very easily, switch easily between the metrics. The 1 minute average, as you can see, is much more spiky than the 15-minute average. Another thing that is also very important to monitor is the thread pools. So the thread pools are not directly related to performance in terms of how hard the machine is working, but it's a good evidence to how well you're doing. Elastic OpenSearch creates thread pools for multiple operations. The most interesting ones are search write, query and write thread pools. Those will basically make threads available for search operations and write operations. Now, let's talk about the search operations, for example, for a second. Let's say you have a machine with a certain number of cores. You have 10 threads available every point in time for running searches. If you have 10 searches per second, each search takes exactly 1 second, you'll be basically using all the machine resources, but everything will just flow nicely because there's enough resources, there's no resources for everyone. The 11th query is going to have to wait in a queue. And so we have this thread pool queue, and we really have to monitor for it, because if it's always busy, it means you're under provisioned, or there is optimizations that needs to happen on the queries or anything else. So that's essentially why thread pools are very important, because if we see the thread pools, search thread pools, for example, is very busy, it means two things. It means, one, search performance is not as it should be. Your users will see slow searches, not because the search is slow, because the system is overloaded. Their search is waiting in the queue before executing. And second, it could be rejected at some point. So we need to do something about that. It basically looks like this, right? So on Pulse, it looks like this. Search queue size, this is some sort of a pattern that you can see here. And if it goes to the limit, there is some upper limit here, you'll start seeing search rejections. So first you want to make sure there is no rejections, and then you also want to make sure that the search queue size is as close to 0 as possible, and then it's your decision. If you want to, assuming we've done all the possible optimizations, we reviewed queries, we optimized everything, we optimized caches, we'll talk about that in a second, and everything, then you need to make a decision. Is this okay for you? Is search performance okay and satisfactory? Or do you want to make sure that no searches are waiting in the queue and optimize searches further but that would probably mean some cluster hardware changes. This is a good example of where adding replicas would have helped, because you would have more cores available to you and more threads. But if you're already fully replicated, then you need to either optimize searches or find other optimizations, or add more cores, add more hardware. So you need to make this kind of decision. Do you want to add hardware and pay more for the cluster, or you're okay with the search performance? All right, so that's the queues. Again, it's the same for everything. Search queues for several all the available thread pools. The search thread pool, search queue is probably the most important one, right? Because it's like the most sensitive. For example, on writes, as long as you don't have write rejections, I don't mind what the write queue size is, because that's okay. It will just be longer to write. It's fine. And even if you have rejections, most writers are able to log stash and data prepper and fluentd and everything. And they know how to deal with those pushbacks from Elasticsearch, from OpenSearch, essentially. So search queue and search thread pool is really the most interesting one, or the most sensitive one to monitor and pay attention to. In terms of memory, and that's also interesting, and then we'll talk about caches, is also an interesting bit. And like I said before, when you do sizing for CPU and cores, you do need to take memory into consideration. Memory is used in OpenSearch in two different ways. One is for the heap size, and depending on what you're doing, you're going to need more or less of heap, of the Java memory heap. And some operations in OpenSearch are not using the heap, but and actually using the native memory of the machine. So if you do a lot of aggregations, you'll actually gain a lot from memory that is not assigned from the heap, via, for example, the page cache, file system cache, often called, and others, so off-heap data structures. So it really depends on what you're doing with the cluster to understand exactly how to fine-tune that. The recommendation usually, you can never go up above 30 gigabytes of heap, and never above 50% of the machine, of what the machine has, because of various things that go on. If you do that, then you have some performance penalties. So if you stop doing that, you should see better performance. And then again, you probably need to add more Java heap memory by adding more nodes, right? Or there's room for you to gain from performance improvements by adding more native memory that is not assigned to the heap. But that's again, so page cache is this concept of disk file, like blocks in disk being mapped to the memory, so not to the Java memory, to the machine memory. So when certain blocks in disk are being accessed very frequently, you start getting access to them from memory itself, not from disk. So that's one of the benefits that actually happens, and there's ways to monitor that on the machines. And JVM heap is where data structures that relate to searches, to aggregations, to various operations that OpenSearch does under the hood. And we also need to monitor for that. Basically, if you have, this is how Pulse shows it, the memory heap usage. And if you have a certain memory assigned, the graph should look basically like that. I'll show you a different graph in a second where it's unhealthy, but this is pretty much healthy. It depends on the GC algorithm used, but basically this is healthy. This is sometimes it's being freed up, cleaned up. The baseline is solid. It's about 75 or 85% of the available heap, allowing it for some headroom, but then that's a good graph. Those downs, the spikes down that you saw, this is basically garbage collection, the GC. I'm not going to go into how GC works exactly, but the idea is that we're going to clean up objects and free up space. And we want to also monitor GC. We want to make sure that the GC, first, most of the GC cleanups is going to happen on the young pool and not the old pool. All right. Old pool GC often signals some performance penalties and issues. On the young pool, we expect to see that GC cleanups are quick, right? Dozens of milliseconds, not more than that. And this is also from Pulse. This is how we monitor it there. The memory issues will cause circuit breaker issues. So maybe you saw that before, circuit breaker tripped, and that's basically some protection measures that OpenSearch has to ensure that the system does not crash without memory errors. But those trips by circuit breaker trips are not fun either. They will reject queries or other types of operations, and it looks like this. So that we monitor the parent. This is part. There's a couple of circuit breakers to monitor, but we monitor this is how the parent one looks like. And this is how a heap space usage looks like. You see a spike, and then you see a trip, and then start being rejected, and Pulse will alert you on that. It will trigger an alert when those things happen, and we'll need to monitor that closely. There's other circuit breakers like field data that is being used in aggregations and request circuit breakers and so on. Usually you will see issues with the parent one, and that immediately translates to heap space issues. You don't have enough heap space available. We're also monitoring caches in OpenSearch, and OpenSearch has, other than the page cache, it has 3 types of caches: the request cache, the query cache, and the field data cache. Request cache and query cache are probably the most important one, and monitoring that is a crucial piece of what we do. We want to make sure that we really use all the available memory, and that's how it looks like. We monitor the hits versus misses. Hopefully, we want to see that we have many more hits than we have misses. It really depends on usage. There's not always things that you can do with it, but if you have a lot of misses, maybe there's things that you can do on the query side to optimize. Not necessarily, but maybe you can optimize some query writing skills to get more than that. And this is how a graph that is not too healthy, to be honest, because you can see the amount of evictions that happen. So when you see a lot of evictions like that, in this case in the data nodes, and that the memory usage is plateauing, so you have a flat line on the memory usage, and you still see a lot of evictions, that would tell me that we could use more request cache. So we would probably recommend that you increase the request cache. Again, looking holistically, maybe there's other things at play that would prevent us from doing that, but that would basically be a recommendation in this case. Because as you can see, we can use more cache and then it will probably improve performance. The amount of misses and hits is not that big, right? So it's not critical recommendation, but still something that based on those 2 graphs, something we would recommend. It's going to be the same on query cache as well. So the difference between request cache and query cache is actually usually more important sometimes. It will basically cache individual pieces of queries that repeat themselves within queries. And then basically, as you can see, there's more memory assigned to it by default. It's actually more important, going to be more usable. And we would first probably prefer to increase the amount of cache used here. And depending on amount of misses and hits, obviously. But again, those things we want to monitor closely and then make a decision based on the rest of the things that we see around. The last one is the field data cache. To be honest, it's less interesting a lot of times, but when we do see very high usage of it, it means that there is probably some room for optimization on the query side. It's aggregations that are done on high cardinality fields or other misuses sometimes. So if we see some graph with high eviction rate or very high usage here, we would want to look deeper into queries. So that's that. In terms of network, you can see that we do graph it like this. We do that. You'll have limit of 100 megabytes of request payloads, and you'll get payload too large when you have that, and it should be monitored. HTTP compression can definitely help with that, and that's essentially how you monitor that. And similarly on disk, it really depends on your disk performance. If you have locally mounted SSD disks, the throughput and IOPS will not be a worry. But if you have a network disk, then you do need to keep track on that to make sure that the throughput accumulated write and read in terms of kilobytes and the IOPS read and write are not above what you have provisioned with the disk. Also something to keep in mind. This is not something that pools sees. So pools can report the actual traffic used, so IOPS and throughput, but we don't know what's the cloud or the infrastructure limitations are, right? So we'll need to rely on you on that. And there's alerts that we can set if we wanted to alert when that goes above the threshold. Trivial, how many indexing and search operations are happening in the cluster. Every cluster behaves differently, but the way that we let you do that is we look at the average usually, but then the maximum is also interesting to see the peaks and to see how different the peaks are from the average. Again, very easy to monitor that. And then shard hotspots is something that's interesting to talk about as well. When all things are aligned and the same, so when you have the same data nodes configuration, the same disk space, the disk size per node, Elasticsearch and OpenSearch will try to balance the shards, but the main deciding factor would be the number of shards per node. So OpenSearch is not going to, on its own, to balance shards based on the number of search operations and indexing operations that each shard or index has, but only on the number of shards. When there is some disk issues, I don't know, is disk filling up or something like that, then we will get into a float stage, or we'll basically trigger some sort of a decider within OpenSearch that will make sure that at the beginning no new shards are assigned, and when there is not enough disk space, it will start moving shards out of the node. Okay, assuming it's not filling up too fast. But other than that, the main balancing factor would be just the number of shards. That means that we can see imbalance on nodes in terms of search performance or indexing performance. That's something that happens. Usually OpenSearch, when everything is normally distributed, it's usually everything is okay. Some imbalance is fine, but we can sometimes see some acute imbalances on those. Another thing we want to look at is segments and merges to basically, for example, look that merges are happening and happening healthily, and the number of segments is pretty much stable over time, and that the merges actually help keep it up in shape. Usually that's the situation, but sometimes bad things happen and it's not, so also something to monitor. And this concludes our discussion on OpenSearch cluster monitoring. If you want to try out polls to monitor your own cluster, wherever it is hosted, go ahead and sign up. It's free to try out. In the next session, we'll build on the knowledge from this session and look at common OpenSearch issues and how to handle them.